差不多。我上网上教我们稍微快一点哈，所以我中间想说查一下这个稍微再把advanced speech recognition 的一些 history 稍微再讲一下。那下一段我们再开始拉回原本的课程的主轴，那些 acoustic model 的一些模型的学习这样子。OK，然后这份 slide 其实我从别的地方拿到，那是这个在 IBM 他们在做一个 ASR 的 lecture 的时候，做的几份 slide，那其中一开始有一些 introduction 在讲一些 automatic recognition 的一些背景啊，那我就跟大家分享。OK，alright, so we'll continue. Okay, so I'll do a brief sort of a history intro to ASR. So nothing technical today. It's more of an overview. Okay, so next week we'll come back and talk into the actual mathematical formulations of speech recognition and things around that, and the hidden Markov model and so on. Okay, so again, since we're into the speech recognition, I want to make it clear, right? This is converting speech to text, so that's what we call ASR, automatic speech recognition. It is not natural language understanding. It does not understand the word. Okay. It is not speech synthesis. That's what we call converting text to speech. It does not recognize who is speaking, so that's speaker recognition. So speech recognition, automatic speech recognition. A better word for that is a speech to text transcription or a speech to text translation. So taking a speech signal into a set of written symbols. Okay, but the machines do not understand those tasks. Just it's a pure mapping between continuous signal of speech into a sequence of symbols. Okay, so sorry, why is speech recognition important? Again, one say because it is fast. Okay, there are different modalities that we human uses to transmit or actually receive messages. Okay, and smell is one thing, right? You spraying yourself with perfumes, approximately less than a word per minute. Taste, you're dipping yourself in a different flavor, and then also less 1 word per minute. Touch, you can touch, you use mouse. Okay, and you probably can do 60 words per minute, maybe. Okay, sight, you do sign language gestures, using all your hand gestures to talk without a speech. You can probably do about 100 to 150 words a minute. Okay, speech with the modality is a sound. Okay, the method, this speech, the rate can be 150 to 200 words. So across all the modalities across all the senses and modalities that we human have, okay, speech is probably one of the fastest encoding methods across all modalities to transmit information. Okay, a lot of times processing speech is faster than processing text, right? So you just need to speak. You don't have to type. The typing, right, really is about 60 words per minute at the fastest. Also, speaking require no hands, right? So you just need to speak, without doing anything. Move your mouth, message comes out from your mouth. Okay, you don't need to have any other tools that have been designed so that you have to, use your hands, use for typing, use whatever stuff that actually make things work. Okay, well, those are good. And then lastly, it's the most natural form of human communication. So if you want to try to process some signal out of a humans, you want to process their speech because they include the most information, the most natural form. So again, today basically I'll talk briefly about this speech recognition from around 10,000 feet up. Okay, where the next lecture will dive into the actual details about speech recognition. We'll talk today also a little bit brief history on speech recognition, what has been done and what's the current status of speech recognition. Okay, so what's the basic goal, right? The speech recognition trying to recognize or output as many words correctly as possible. Right. So again, think about like the reference for the right word, right? The cat in the hat, right? So so if your speech recognizer outputting, some hypothesis, right? You're outputting the hypothesis that the cat is on the green hat. So the correct one is the cat in the hat. Okay, hypothesizes cat on the green hat. Okay, so you have these two sequences. Okay, how do I measure? Okay, sorry. How do I measure how do I come up with a metric to talk about the error this metric? Okay, so this is what we call a word error rate. Okay, so if you know machine learning, we always talk about the accuracy metric. Okay, this thing is accurate, the precision, the recall, all those metrics. Okay. Our speech recognition also has its own metric, or this metric called word error rate. And we have to look into it deeply, right? Because you have two sequences. This is the correct sequence, is a hypothesized sequence. There can be three kinds of error that exist when you compare two different sequences. One is called deletion, right? There's a word that needs to be here but disappeared. Okay. There's a substitution. Okay, this is the word in, but you somehow recognize it as this. Okay. There's another error called insertion. There's no word here, but somehow you have a word called on here. Okay. So when you compare two sequences, how accurate they are. Okay. The accuracy metric or the error metric actually includes three different errors. So the error is, in this case, it has one substitution error, it has one deletion error, it has two insertion error out of all the words that it has, right? 1, 2, 3, 4, 5, right? The right word, there are 5 words, okay? Out of those 5 words, you somehow delete one word, you insert 2 additional words, you change one of the word, okay? And add it up, and then you get 80% error, okay? So in this sentences, right, the right sequence is the cat in the cat, okay? That if your speech recognition system gives you cat is on the green and the error rate is 80%. Okay, can this error to be over 100? Yes. Okay, you can insert many errors here, and out of the words that you have, divided by that number also. So as long as you have made over 5 errors here, your error is over 100%. Okay, so word error is a different kind of error metric. You have to be aware that's being utilized in our speech recognition system. Okay, so a lot of algorithm that we develop in ASR is trying to lower this word error rate. Okay, so this is kind of the gold standard metric that people try to assess how accurate a speech recognition system is. This metric is imperfect, but they're very useful and simple to measure in terms of objective criteria. Because if you look at, if you just look at it from your eyes, it doesn't look that wrong. Okay, I mean, you have the cat out, you have the hats right, the is right. Additionally, insert a few words, but overall that error rate is 80%. Okay, that's pretty high. Okay, so it's actually pretty stringent when we want to make sure our speech recognition works. This error rate needs to be low. A kind of a take-home message. Okay, if you human error rate. Okay, that means if I actually know the right sentences and I ask a human to type the sentences by hearing, human error is about 5 to 4%. Okay, word error rate. So human isn't perfect as well. Okay, if you listen and type, okay, it's about 5%. The current nowadays in a large scale data set with very clean speech, okay, the current ASR can go also below 5% error rate. And many of the times the ASR system in the wild or in actual commercial system that works, usually they sit between 10 to 20. Right? That's the word rate that actually make the system workable. Okay, so if you have over 20% of word error rate, those systems will start to lose its ability to make it downstream. Okay, so keep this in mind. This is the way we compute the error in terms of the ASR. Okay. All right, again, I want to show why this ASR difficult because speaker verification, you and me, we're two different speakers. Okay, we speak very differently, but if you hear the sound, they are the same sequence, right? Channel variation, if you're speaking through this microphone, speaking through your cell phone, speaking through a landline, all those things create a different characteristics of the sound. Okay, but they all sound different, but they all have the same words. Okay, so that channel variation also be involved. Background noise, okay, we know that. Accent also difficult. Okay, you and me, we both speak English, but you're from UK, you're from America. If you're like we're a foreign language learner. Okay, we all speak a little bit differently. Okay, but they seem to map to the same word. So every accent also creates a different variation. Okay, in terms of recognition. Speaking style, like I said, some speak very fast, others speak very slow. Those speaking style also creates variation. So what we want to tell you guys is, they are the same words. Okay, they're not single one factor that will create a variation. So there are many factors in combination that creates a variation that you see in that one-dimensional signal. So they all have the same word, but because of all these factors, they will create very different waveforms. And then the goal is out of all those waveforms, we want to map them to the same sequence of word. Okay, which is the most difficult part is that, right? So all these factors will create a variation. All those variations exist in your signal, and these signals eventually have to all map to the same sequence of symbols, sequence of words. Here's just some examples of 1,000 times no. Okay, so just different ways of saying no. Okay, if you look in your eyes, they all look different. Okay, depends on speaking style, how fast you're speaking, how loud you're speaking, the speaking style you use, where you are. Again, all those things are the same word, but if you look at the form, they all are different. Okay, so again, if you take a look at this inherent variability of the speech is the again biggest really the biggest challenge, and another variability comes from the durational variability. Okay, every word you speak it's not just the way you speak is different. Okay, not just the loudness, that feature value is different. It's even the duration, right? If you're really fast, you're a fast speaker, the you speak will be very short. Okay, you're slow speaker, the will speak very small. Okay, and then you are female, maybe I'm male. Okay, then my already have feature difference. Then if you're a speaker that speak fast, speaker that speaks slow, that duration is so different. So it's not just spatially that the feature value are different. Temporally, they are also different. Okay, so think about this very complex phenomenon of we trying to map a sort of a continuous speech waveform to a set of symbols of word sequences. Okay, and when everybody, because of just you are you speak differently, and that speak differently has two-dimensionally differently. One is the actual value that you generate will be different. The duration that is generated will be different. And then these two things simultaneously happen. Okay, so because of all the factors that we just mentioned, okay, which that's why speech recognition is one of the early tasks where a lot of the major learning algorithm, a lot of the major sort of core algorithm for many other applications you have seen develop from speech recognition system. Okay, because it's a very complex sequence learning of variability learning. Okay, so it's the first. So now that people know convolutional neural network, right? So it's just like an image processing task. Okay, the very first paper that Young and Kuhn published is in speech, where they use convolutional neural net to model the speech sequences. Okay, it's the same because it's trying to again model this durational difference in terms of sequences that's been, back in the 1990s something they found, okay, convolutional net seems to work good there. And then imagery will look at it and apply to them with the large data they have. Somehow it works very well for them. But a lot of the application, sort of core algorithm really comes from the speech community where we first look at very challenging problem here. You can imagine there's countless ways you can speak a particular word. All these countless ways of speaking a particular word, they vary in duration, vary in the way you're speaking. They all have to map to the same word. Okay, that learning itself is very difficult. Okay, so and that learning is also depends on the data you have. So the kind of data-driven learning approach starts, and a lot of it in speech recognition community. Okay, so keep that in mind. Okay, I think we talked about this last time. We'll again drill down per. So again, finding the ASI is really trying to choose, right? Because you have a set of symbols, W, okay, out of the W set. Okay, you choose W to maximize this particular probability. Okay, so given the A, we call it observation, or we call it extract feature from the speech signal. Finding the set of W that maximize this probability. So knowing the thing I see, what would be the good set of W out of the W superset that would maximize this probability. And this can be computed as this true probability using Bayes rule, right? So that's for probability A given W times probability W. What's this thing we call an acoustic model, or it's a statistical acoustic model. If I know which word you're speaking, I can compute the probability that I see those features coming out of that word model. Okay, that's acoustic model, right? So for acoustic model means every category of sound, okay, there is a probability I will see the feature distribution like this, right? So given that known word, what's the probability of me seeing the things I see those features? POW, we call it language model. What's the probability of that word in existence? Okay, without knowing it, right? Without actually looking at the signal, what's the probability of that word would appear in this particular language? That's why we call this language model. Okay, in English, the I is those things can happen a lot. Okay, so that probability of those things appear naturally will be higher. So if you somehow have a system that that somehow confused between two different acoustic model, but one of the words more likely to occur, then that will shows up, and then it becomes the most likely P of W given A, right? So ASR is basically it's all about finding W that maximizes. So W we call it back vocabulary. Okay, it could be phoneme, it could be word, it could be diphones, it could be triphones, it could be in Chinese, it could be syllables, subsyllables, subwords. Okay, it depends on where you break your chunk into the homogeneous distinct unit. Okay, so we call it vocabulary. A observations, usually there are features. Okay, the things you actually compute on the signal. Okay, as the features that you represent when you see the signal. P of A given W acoustic model, P of W language model. There's a thing we might not be able to touch in this course is hypothesis search. Okay, meaning because there's so many words that could happen over the entire sequence, right? So every segment in time, there are all these different models through the sequence of word, right? So you're basically looking at okay, what's the likely word here, what's the likely word here, what's the likely what's likely word here. Out of all the possible word sequences over the entire sequences of the speech sound, that search can be very tedious. Okay, it takes a very long time to search. So the best word vocabulary set across the sequence. So there's also efficient ways of trying to search through those sequences to make sure the final sequence of word that I shall output from this this audio file is the best word. So we'll touch a little bit on that, but we won't go into detail. So even the search itself is a problem in ASR, okay? Because you want to do it fast, okay? Make sure the sequence of word that I found that can maximize P of W given A is the best and the fastest way to get that sequence of W so that P of W given A over the sequence of audio waveform is the best one. That's hypothesis search. Okay. That's sort of a speech recognition from 10,000 feet up, right? So the next course, we'll start here, probably the acoustic model. Okay. And we'll see that there's a particular model people will start doing and trying to handle the exact thing that I was saying. The variability exists durationally and spatially. Trying to make sure the model can have the variability handled across these two dimensions. So even though if your sound can have the durational variability and also spatial variability, I can handle those things that give me the right probability to distinguish between this model and that model. All right, so let's look at a brief history of speech recognition. 30 early days, okay. This thing can go back to about 1950s when people started to look at problems of automatic speech recognition system. Okay, this is what we call ad hoc method. Okay, there are many ideas that are introduced. Ad hoc meaning someone designs certain rules. Okay, if you look at certain rules, the things that appears, it probably means this is that word. Okay, so many ad hoc ideas now used all together. A lot of times they do some spectral analysis, some version of statistical training, language modeling, and then what we call all those work mostly in a small vocabulary setting. There's only a finite, very small set of words that people can recognize. Digits 0 to 10, okay, yes and no, okay, or vowels. Okay, so it's not like me speaking continuously with different words. I'll be able to do this thing what we call large vocabulary on my speech recognition system. But back in the 1950s, they're all sort of a small vocabulary. They are also not tested with many speakers, usually less than 10 speakers. But that's where people start to look at the problems of automatic speech recognition as a sort of template matching kind of problem. Okay, about 1970s, 1980s, there's a birth of a modern ASR system start to come kind of come in shape. Okay, there's a very famous quote, okay, also from a researcher from IBM, basically, every time he said, okay, every time I file linguistic, the performance of speech recognition goes up. Okay, so what that means is start to slowly shift from domain knowledge to data-driven approach, right? So when previously it's about let's ask linguistics, that word has WR earlier, right? So let's look at R now add linguistic, okay, where the format comes about, okay, is this the right format? Okay, if you are male speaker, female speaker, does your format move? So we keep asking linguistic about this knowledge about the acoustic signal relate to individual sound, and we kind of write that knowledge a set of rules, kind of technology to be able to do ASR. But I think in this particular case, we will start, okay, to ignore almost everything we know about phonetics, linguistics. Okay, it purely make this speech recognition system as like I said, finding most probable word sequence given audio. Okay, and this particular idea, turning the problem of taking at the knowledge, looking at knowledge writing rules, now say, okay, let's make definitions of ASR as a probability problem. Okay, finding the most probable word sequence given audio. Then you can train those probability or you can estimate those probability with transcribed speech, meaning you start collecting data, a lot of data, looking at their label, okay, the right word, okay. You train it, that means you start estimating, you statistical estimation on the probability distribution. Then you can do this finding the most probable word sequence given audio. So this is a turning point where we start treating ASR as a nowadays we call it a learning problem, or nowadays we call it AI problem, right? So make them like an AI problem instead of encoding linguistic knowledge about the word. Okay, this is the time that probably back in the 1970s. Okay, so okay. Basically, 70s to 80s, that's where many of the key, most important algorithms have been developed, okay, and refined during this time. We'll talk almost everything here, okay. Many key algorithms define expectation maximization algorithm, okay, we'll talk about that, okay. It's an estimation method to estimate the probability of a statistical model where you cannot find a global solution. Okay, so you use an EM approach to do that. N-gram models is a particular version of language model, okay, where the framework depends on the N passwords, okay. That particular Markov chain kind of idea come into the language model. We'll also talk about that in this class. Okay. Gaussian mixture model. Okay, we say the features. Okay, when you have R and R, okay, they are not the same in the feature values. They won't be the same. But how do I model that differences? Okay, we can model that differences like a distribution of the Gaussian mixture model. Okay, so that is Gaussian mixture model also being used. In the Markov model, the core of the core behind the modern ASR system, right? It's a Markov model, so it's a time series model. It helps you encode the durational differences. When it combines with the Gaussian mixture model, it also helps you capture the feature value differences and the durational differences. And these two things combined become the backbone of the most of the current modern ASR system kind of thing. Okay. Then there's a Viterbi decoding. Okay, this is a particular method that have been designed in communication system. Okay, the original goal was to say, okay, when I transmit a set of 0 to 1 to the other side of a receiver, then it will be quickly decoded through the receiving messages. So I know what the most likely 0 and 1 has been sent to me. Okay, that was originally designed in that Viterbi decoding. It's used everywhere now in your cell phone. Okay, and that particular approach has been applied in terms of trying to explain and then learn the Hindenburg model, Gaussian mixture model, this kind of ASR system. Okay, so we'll also talk about that. And this Viterbi decoding is also the algorithm algorithm is behind the scene of finding the most probable word sequence, right? It's decoding through that word, decoding through the original file to find the most probable word sequence. It's like finding the most probable zero and ones at the communication receiver side of things, right? So we utilize that kind of algorithm also in ASR system. So anyways, all the things that you see here, okay, we'll cover in the next half of the course. Okay, so everything in here, and then the newer approaches are basically a refinement on this particular concept of finding the most probable word sequence, okay, given an audio file. Okay. Even till this point, when we have deep learning age, okay, what we're doing ASR is still completely based on the concept of finding the most probable word sequence, okay, given the data that we have. But at that time, it's in the 80s, okay, there not as many computing power, okay, compared to now. Okay. One of the first real-time system was built in IBM in 1984. It needs a very specialized hardware at that time, very top of the game, right? 60 megahertz painting, right? So at the time they used this kind of a CPU to run ASR system. All right, then we call the golden years, 1990s to now. The now in this particular slides are about 2016, 2017. Okay. In 1994, the CPU speed is about 16 megahertz, right? Now it's well over 3 gigahertz. Right? Training data at that time is less than 10 hours. Nowadays, any serious company that's doing ASR system, they have over 10,000 hours of data. Okay. And 994s, they have Gaussian measure model as an output probability they use, okay, which model the feature differences between the same sound, okay. Now this use kind of a neural network plus PNN kind of a combination hybrid form to make it even better. The sequence model at that time, they were using HMMs, okay, at the 2016, 17 is still largely based on some HMM system, okay. Nowadays, somewhat still, okay, if you want to do a real-time processing, HMM still has to be, if you want to do batch processing, you don't have to HMM, you can do neural network based, but if you want to do real-time stuff, HMM is still quite useful even back in 2016, okay. So the language model, 1994, they used Ngram, and now they still use Ngram, okay, well, with a slight version of, inclusions of neural network to help them, okay. So what we see, 1990s to about 2020, okay, that's 30 years, okay. Basic algorithm have remained very similar, okay. What you probably see is a lot of the penetration of utilizing neural network to help guide the entire learning to make the performance improve a lot more. So significant performance gains can also attribute to the presence of more data, faster CPUs, faster GPUs, and a lot more runtime computing memories. Again, this is at the cutting edge. Okay, nowadays computing resources is huge among us. Okay, lots of training data, everything. Okay, I mean the algorithm has all become very sophisticated, but all still very dependent on this kind of back in the days 1994 HMM kind of architecture. Okay. All right, so here are some ideas. So if you do a connected different task of ASR, connected digits, right? Those things 1, 2, 3, 4, 5, 6, 7, 8, 10. Okay. Machines can do at that time about 0.72 word error rate. Humans are about 0.009 word error rate. Okay. Letters A, B, C, D, E, F, G, all the way to things. Okay. Humans about 5% error rate. Human about 1.6. Resource management, human machine 3.3%, man 0.1%. Wall Street Journal, okay, machines at that time about 2%, 0.9%. Switchboard is a corpus of conversational speech. Okay, me talking, you talking. So the grammatical structure is a little bit more loose. The way we talk is more free. Okay, not as natural. It's more natural, more spontaneous. Back in about at that time switchboard about 40 something percent. Back in 1997, human about 4% as well. We say the humans probably we're up running about 5% with a very complex kind of a recognition task. Our ability to be able to recognize about 4 to 5% for error rate. what you see here, one thing you can clearly see for humans, okay, we have one system fits all. You have one single ASR system in your brain that works for every single task, and all works all very well. Okay, for machines, okay, you have things can go from point something percent all the way to 40% error rate. Okay, so we don't have a generalized ASR system really at this moment. Okay, we have many specialized ASR systems that works across different contexts quite well. Okay, but unlike humans, okay, we humans are incredible. We have one single system that just somehow works quite perfectly across various conditions, almost without training. Okay, so that's the thing that we are very capable of doing. Okay, right now I throw you in a highly noisy condition where you never been to the condition, you are still be able to recognize the speech there, almost without any training. I don't have to retell you how to learn that language. You can still understand Chinese and in a very loud background noise. Okay, so this human capabilities of processing speech is still, I think our machine is trying to catch up. But nowadays, right, switchboard they can push this down to 8%. Okay, but that's with 200 hours, 2,000 hours of switchboard training data. You always can't assume that's always available. So the slide here is want to tell us that when you look at the way that the modern ASR system works, is we train on tens of thousands of hours of data. It slowly start to match how we humans, okay, be able to do speech recognition. But think about the number of hours, okay, that it takes a child to start speaking, okay, and recognize speech, okay. Definitely not 10,000 hours, okay. You don't even leave that many hours in your life, okay. So a couple of years, and you don't expose to all that audio sound, and nobody's teaching you, right? So we don't have a supervised learning kind of a framework, okay. And by somehow that learning, we have a machine, we have the automatic machine system in our brain that works the entire life, fits all conditions, okay. And our machine nowadays, the algorithm that we're developing, requires tons of data, and only works sort of okay in a particular specialized task. So we're still far away from how we humans are capable of doing a speech recognition system. So let's just keep that in mind. Although we always say it's AI, kind of outperform humans, but I think in a way have to be very careful. Think about how we really human learns to do speech recognition system. Think back in your days, right? When you're first, very young. Okay, you're not running your system. Somebody teaches you this is that for over 10,000 hours of data, right? And it only works 40% when you speak on the phone, no, right? So it works almost perfectly when you speak on the phone, and you probably less than 100 hours of exposure to speech, then you somehow learn everything about how do I recognize certain speech. So that's something that's very unique to us humans learning versus artificial intelligence learning. Okay. Anyways, that's more on the human scientific aspect of speech recognition system. That's one of the last thing I'll share a commercial speech recognition system about 1995, 1998. The first large vocabulary speaker dependent system are being first deployed. Okay, the key thing there is speaker dependent. Okay, so you get rid of the variability between you and me. Okay, but if I know everything about how you speak, I can work it out for you. Okay, so usually during those times you have to ask the speaker to speak multiple times into the system, so they kind of adapt to you. Then it only works for you. Okay, so that's a little bit in RP. So to the beginning of the 2000, the first telephony-based customer assistance system was starting to be deployed, where you make a phone call, okay, and it calls in, and they actually be able to assist you by understanding what you speak. Okay, it's difficult because the telephony-based system, meaning the audio, the signal that you're sending through all this landline with various channel effect, right? Different switches, okay, of your communication parts, so that you can connect here to that point. And the sound has been distorted a lot. Okay, so those and they all have to do it in a really fast manner. About 2000, 2007, okay, the Porsche automotive interactive system where you actually can now speak to your car and say, okay, turn on the AC, okay, turn on the light, okay, turn up the bell, okay. That's when actually actually in car, you have limited computing resource, and then it's be able to spot what you want it to do, right? That's kind of a modern system. Okay. 2008, 2010, you start have the first voice search system. So the difference between here and here, this is open air, right? This is closed setting. Okay, in a car, you have things that's for enclosed, enclave in a car kind of structure. Your voice search, right? You can have your laptop, your cell phone, anywhere that could happen. Okay, so this is a much more difficult task than this. This is a noisier task than this. So again, we started to see this commercial system that start to roll out, trying to handle more and more complex system. Okay, nowadays it's all cloud-based solutions, right? So you have cloud that's sitting in the cloud that has tons of data that's been trained, very large models, and then your cell phones here or everywhere else, at some point it's gonna send a request to the cloud and try to do all the speech recognition system in the cloud and then send it back. So nowadays a lot of these are cloud-based speech services. And of course, things goes right because the deep neural network can be very large. Okay, you can train on. It's no longer just 10,000 hours right nowadays. They're training like 100K. Okay, 200K hours of data. Okay, those are humongous amount of speech data that's being trained in the current modern ASR system that's trying to tackle all sorts of language problem. Okay, and even in a multilingual kind of perspective. So things have changed, right? So, but the core algorithm hasn't changed much. Finding the most probable sequence. The real thing that makes it works better is our computer resource has boosted up. The ability to get a lot of data has been boosted up. Okay, and be able to train a system in a time that's manageable. Okay, then these two things combined, okay, makes the actual system start to work quite well. Okay. But the bottom line, okay, the problem we're still trying to solve, that sequence matching of this acoustic sound to the set of symbols still remains very important. I think that's the last slide. So again, that's the brief histories of ASR. I hope that you guys kind of know. But back in the 1950s, okay, at that time, speech recognition is probably one of the first work, okay, that really, now we say this is an AI approach, right? But back then we don't call it AI, it's a statistical data-driven approach to look at a problem from a technology perspective, okay, right? So understanding speech, then we're building a speech technology called speech recognition system. The most natural version people first do is engineering, go back to linguistics, tell them, hey, linguistics, tell me which sound has what kind of properties. I'll just write out using a code and try to write out this property as rules. But then they quickly realize there's too much variation across everybody, every condition, everything that you can compute. Okay. Then later, right, the paradigm has shifted. It has shifted from, let's really look at the core knowledge of linguistic. Now we call, it's kind of loosely inspired by linguistic knowledge, but what I'll do is start collecting a bunch of data. I'll treat them as a statistical sort of probability estimation problem. Once I take that approach, right, it makes the speech from a linguistic problem to a statistical problem. So that paradigm shift, okay, once that's been shifted, okay, the technology start to kick off, okay. Then people start to develop all the core basic algorithms and make sure we're able to train for a large amount of data, handling variability of the speech, formulating speech recognition tasks, not a set of linguistic knowledge to rules, more as a finding the most probable sequence. Okay, again, you may find it's trivial, but this is really the tipping point where we take a problem from a linguistic knowledge, a scientific knowledge, and ask the problem to say, okay, instead of asking the problem in terms of linguistic knowledge, we ask the problem in terms of probability. Once we ask the problem in terms of probability, it becomes a technology problem, it becomes a mathematical problem, it becomes kind of what we call a learning problem. Then when you ask a problem that way, there are many things that being developed, many works that's been developed. Okay, so and then things to flow really fast. Otherwise, we are unable to understand, right? People know if you ask a linguistic, the word okay, just the if it's the previous word if it's p, pa, or if it was with R, okay, that R will be different between R, P, and P, okay. So, as a linguist, have your rules, okay, which phoneme come before R would change the formula of this R to what thing, okay. That knowledge is not going to be quick enough to be able to handle this, right? Female has a different R, the male has a different R. When I say an R into a open space and a close-up microphone, they are different formats. So you cannot exhaust every condition to be able to understand just a simple sequence how that features will change. Okay? So when we eventually kind of people just give up and say, okay, let me just go out and collect a bunch of data and try to understand. Okay, out of the data, let the data tell me how R can be. Okay, then once I let the data tell me how R can be, then I formulate the problem that way, and then things become easier to handle, things get faster. And then 1970s, 80s, that's where we'll teach you guys the algorithm that we developed back in the 80s. Okay, HMM, so vector decoding, Gaussian mixture model, and all those things. And building upon that structure, okay, then neural networks start to appear. Then it'll change some part of that structure. Okay, but the main thing hasn't changed. You change parts of that structure. Then once that parts of structure changes, because neural network has the ability to model certain probability distribution better than what we previously have, then you combine this the effort between the two, and you suddenly see the performance become very usable in terms of the technology. Okay, that's kind of the progress. So in this pre-class, we'll talk about that 1980s kind of algorithm. In the lab, we'll teach you that toolbox is where it's a hybrid version of that 1980s and the version of a neural network that will work for general ASR systems. And that nowadays, till this point, I think a lot of the ASR systems still build upon that structure. Okay, although neural network is very large now, works very well. But the problem at the deployment at the commercial product stage, some of those very heavy ASR systems still not workable. Okay, so you have to go back to what's really working throughout the years that people know. So we'll again walk you guys through all those approaches. OK， 好，我今天就先讲到这边，就是一些背景知识。那我们下一班就开始进入。